This circuit doesn't have any active sources, so it's not a real circuit we can analyze, but still demonstrate the typical writing of the equations. We're going to use current that exits the node is positive. Current that enters the node is negative. We also assume that V1 is more positive than the reference. We also assume V2 is more positive than the reference. So now we're using V1 is some kind of positive voltage. V2 is some kind of positive voltage. V1 may be greater than V2 or less. V2 might be greater than V1 or less, or they might even be equal. We don't know. When we work with mesh analysis, it's the same thing. We draw our whole flow arrows clockwise. We don't really know the currents flowing in a clockwise direction until we get our numerical answers. So based on all of our approach assumptions, we are summing currents at the node V1 or in the V2 node, and we aren't really using Ohm's law. We're summing currents. So we have V1, this is a positive V1 over R1, not just the positive of the summation, but because current is exiting V1, this is positive. When we write the term going this way that involves R2, V1 over R2 still exiting node V1, but V2 being positive itself is causing current to enter the node, so V2 over R2 is a negative. And the same reasoning we use here when we look at the V2 node. V1 is entering the node, it's going to be negative. V2, of course, exiting the node is positive. V2 with R3 is going to be positive as well. When we look at this, we say, well, we could have written the equations like this. And we can actually see, yeah, these are equivalent. We could have written them like this directly. This is typically how they're written. This way is more adaptable. We see our variables, V1 and V2. And these are more adaptable to substitution into a matrix to solve a system of equations. Some of the books eventually show them like this. They might start like this. If they're going to solve with a matrix, they eventually start to make them look like this. But we can just go directly like this. We don't have to start here if we don't want to. So there's always more secrets of equation writing, at least of the writing of the initial equations. These are the two initial equations. These are the two initial equations. Just a few more comments about the previous frame. Again, just repeating this format here. Talk about when we're at node V1. And we can see here, as we already assumed, Vn, or the node voltage, is more positive than the reference. Vn is like a voltage source. And because we're using current exiting the node is positive, it automatically allows us to write more positive terms for the node we're working with. And then any adjacent node is going to have to be negative because this is also more positive. V2 is more positive than the reference. So it must be pushing current into the Vn to the V1 node. So it's entering, it's going to be negative. And when we're working with the V2 node, which same thing, V2 is pushing current out of the node, so it's positive because that's what we want. Positive is exiting. V1 this time is still more positive than the reference, but it is pushing current into the V2 node, so it has to be negative because it's entering V2. So this just is like a natural conclusion. The other format at the top of frame 1 seems to be the way most of the books want to start out doing it, but sometimes they show it like this. this just seems to make a lot, it's just easier to see. We have our V1, we have our two variables, and this format is more adaptable to substituting into a matrix if we want to solve 4 or more simultaneous equations. This circuit has an active source. We can actually analyze this. We're using the same analysis approach as what we already talked about. And here is the initial equation. Except Vn is more positive than the reference, because that's what we assume. We don't know it's really true until we finally get some numerical values, but for now, and we also have positive, current exiting the node is positive, any currents entering the node are going to be negative. And this is the conclusion. We have V1 forcing current out of its node through R1 and R2, and the Vs source, this is actually a plus here, and it's going to actually be a minus here, really. This voltage source is pushing current into R2, into the node, so it's going to be negative entering. And then we can rewrite the equation to solve for the Vn node. Again, we're really not doing much with Ohm's law here. Here I'm going to write the initial equation using the given polarity across R1. And we can see that Vn is actually across R1, and because of this is a plus and a minus, because we assume Vn is more positive than the reference. So we know VR1, if we ran a KVL around this is the result. VR1 is equal to a negative V1. And with the polarity like this, we know that whole flow caused that, and it had to be entering the node. So we have a negative here. And again, these two are positive. And as I say here, this kind of breaks our consistency of how we're going to write the equations, always summing everything with positive terms. Oh, of course, except for here, this is the format, but this time we have a negative here. So yeah, it's a little more difficult this way, but because VR1 is a negative Vn, when we substitute this, we end up with a positive Vn over R1 and a positive Vn over R2 anyway. Exact same conclusion. And the Vn voltage happens to be, well, it's a voltage divider. And if we rearrange this, just curious, it looks like the gain of a non-inverting op-amp, except the gain equation is in the denominator. And of course it acts as attenuation for a voltage divider. This circuit is from a book. I added this 20 volt voltage source to change things up a little bit. Notice that this one is a minus top and a plus on the bottom, so it's not the classic. When we inspect this voltage source, this one's pushing current into the node. This one is going to be pulling current out of the node. We're still using the same initial constraints. Exit is positive, enter is negative. And the Vn node we use it as if it were more positive than the reference node. We don't really know it's more positive than the reference node, but just like with mesh analysis, we don't know current's going clockwise when we draw our whole flow arrow. So it's, and the books tell you that. I1 and I2 are labeled here. Of course, I'm going to do the same circuit with mesh analysis down here. And the initial equation, again, has a familiar format. Here we don't have zero because we have a current source entering the node. Notice the 15 ohm resistor never appears in the equation, and there's a good reason for that. Should be obvious. It's a little test question there. Over here I'm writing the KVL equation around this loop here because I want to solve for Vx. So we write a KVL around here. Notice that the 20 volt source is not in the equation. And there's a good reason for that. So we have our initial equation, a supplemental equation, substitute Vx 100 minus Vn. And we can fairly quickly solve for Vn, and then a substitution back in Vn into here, and we have Vx. Here's the mesh analysis. Here's the initial equation for mesh I1. Mesh I2, pretty obvious here. I2 is equal to the negative of Vx over 14 because I2 is clockwise. Vx over 14 is shown to go into the node. And we substitute I2 into here. And we need another equation. Vx is equal to 8 times I1. It's positive Ohm's law. Our mesh current clockwise. Our mesh current is entering, the whole flow is entering the positive node. So it's of Vx, or the 8 ohm resistor. So it's positive Ohm's law. And we substitute in the Vx here. And we get I1, a little bit, not too much number crunching. We have I1. We can find Vx using I1. Now we have Vx. We can find I2. It's negative 4.8 amps. I2 is, our arrow is clockwise. The numerical value is negative 4.8 amps. So we know that this whole flow is actually going into the node in the same direction that this voltage controlled current source has been set up to do. Here I1 is a positive 8.4 amps, so we know I1 is really going clockwise in the arrow that we used. We can sum the currents at the node. We got two mesh currents, I1 and I2. We want to find I4, and we're going to we're going to assume that I4 is leaving the node. We have to choose something. It's either we use I4 entering the node or I4 is going to exit the node. I've chosen to use I4 is exiting the node. So we're summing currents. This would be a plus I1 plus and a plus. But since I2 is exiting the node, it's a negative I2. We've chosen to use I4 exiting the node, so it's a negative I4, but they're all being summed, and that's why it's written, that's why I wrote it this way. We quickly solve for I4, and we can find a V4, and yeah, even up here, after we find a Vx, we can verify Vn is still 32.8 volts. We could have written this equation as I1 minus I2 minus I4 equals 0, but then we would have consolidated the summation of this. It just shows a little more of what we're really doing. The books would have written this as I1 minus I2 minus I4 straight up, and wouldn't have said, oh wow, we're really summing currents into and out of the node, and we really have a negative I2 because it's exiting, and we really have a negative I4 because it's exiting, and we have a positive I1. We really would have a plus I1 in parentheses, and then we put a plus out here because, again, we're summing currents. It's a summation. Here's another circuit from the book. Non-inverting op-amp, a virtual ground, Vn is 0 volts. Here's the reference. But the book says, and this is what they do to trick people up, they switch up the convention of how we're going to do it. They now done this to analyze this circuit. They say, oh, we're going to have a positive current is entering the node, and negative, if current exit the node, is going to be a negative. And they do that for a reason, because they already know this circuit's been done, and they know that because if we say currents enter the node is positive, we can write more plus signs, more positive signs in our equation. So what's the better way to do it? To always change our approach? Or are we going to do it in the same way every time? But if you wanted to write the equation the way the book says, this time when we inspect the polarity here, we still have positive pushing whole flow into the node, because we say now we want positive entering the node. Here, same thing, plus, minus, the V out, pushing current into the node. Enter the node is positive, So we have a bunch of positive signs in our equation, and we can write the equation more, looks pretty simple, quicker by changing up how they do it. But initially, they don't say current entering the node is positive, and current entering and current exiting the node is negative. It's the other ones I already did. That's how they start out doing it. But along the way, they mix things up. And saying doing this here is kind of unnecessary, because in order to know IZI is entering the node, we had to inspect our V input voltage, and we might as well just write this initially straight up. Using an initial analysis approach, currents exiting the node are positive, currents entering the node are negative. Again, the same circuit. Vn is 0 volts. Virtual ground. Vn is also assumed to be more positive than the reference. And here is the equation that we would write. Again, we see this similar format. Vn, of course, currents are exiting the node. And these two terms were from the other frame, but this time they're negative because they're entering the node, and we're saying, oh, currents entering the node are negative. And we, of course, know that Vn is 0 volts, so this becomes 0. If we move these to the other side of 0, add them here, just basic. It's the same equation. But this is the consistent way to do it if you want to do it the same way every time. But if the book suggests to do it a different way, just to mix things up. But this is the way the book would have said to do it if they would have stuck to the approach. On the next frame, I'm going to use mesh analysis on this. I'm going to go through Vn, Zi, Zf, and Vout for a loop. This is the single loop mesh equation using whole flow. Everything uses whole flow here. And I is our variable this time. We don't have any, we're not looking at node voltage this time. So here's our mesh equation, or our single loop equation. And we solve for I. And we already know that the voltage across the feedback resistor is Vout. When we look at the Vout plus minus, it's across, because of virtual ground, Vout is across Zf. So they are equal. They have, the only polarity we have is the label of Vout. And those polarities are adapted to the across the Zf resistor. So Zf, Vzf is equal to Vout. And here we see a negative Ohm's law, negative I times Zf, because our loop current, our mesh current going clockwise, enters Zf from the left going in, and we already know that the negative node of Vout is on the left side. We're entering the negative terminal of Zf. It's negative Ohm's law. So Vout is equal to this. We can negate the numerator to do the negation for us. A little bit of number crunching, and we realize Vout is an inverting amplifier. Same result as the node analysis gives us. This is a general node analysis. Yeah, general node analysis. There is no reference this time. This uses topology. There's the topology diagram. The dark heavy lines are branches, and the light gray lines are the links, or you call them the cotree. The setup to make the cotree, the pre-analysis is a bit more involved with general node analysis. It uses a lot of KVL because there is no reference node. We don't have any Vn node, a V1, a V2, so to speak. There are 5 nodes here to start with, but because there's a supernode here and a supernode here and a regular node here, we have reduced this down to 3 nodes. And because we have 3 nodes, we can only write one equation less than the number of nodes. 3 minus 1, we can only write 2 equations. We still do something similar. We always add a node. We're going to write an equation for this supernode and for this node here, and we leave this one alone here. we have a voltage fully defined across these two resistors because Vx and Vy are controller voltages for the voltage controlled voltage source and the voltage controlled current source. So these have to be fully defined. There's no definition across this resistor, and there's no definition across this. So when we look and see this resistor is in a link, there's no labeling here. This resistor is in a link, there's no labeling here. If we had a unlabeled resistor here and it ended up being put in a branch, a black heavy line, we would then have to fully define a voltage on a resistor. Then we'd have to put a polarity across it, and we'd have to label it so we could use it in this general node analysis. We also continue to use current when working with a node. Like before, we always want to use current exiting the node as being positive. And because of that, when we write the equation, when we're working with this node, this we're going to use as plus, minus. So when we find this link voltage, we always find link voltages in terms of the branch voltages because we're using a KVL path, because all of the branches have a fully defined voltage. These links are undefined. These are defined because there's a current source in them. So these remain unlabeled because of the current sources. So we don't need a voltage across those. When we're working with the supernode here, we use plus here and a minus up here because we're using current is exiting the node, and that coincides with current exiting the node, and it affects when we write our KVL. We don't have to do that. We could say, well, we could have plus minus when I'm working with this node here, a plus minus, and current's entering the node. Yeah, we can do that. We can still write our KVL path equation, but then that's going to cause us to write a negative sign because the current's entering the node, and then the numerator of this KVL equation, all the terms are going to be swapped, have swapped signs to give us an equivalent result. So when we use current exiting the node as our assumption, that allows us to write more positive terms for the summation, and it's just more consistent that way. We can do things in the same way every time. Here's the initial equation for the top node, the initial equation for this supernode, and the equations look different because we don't have that reference anymore. And again, we are doing a summation, currents exiting the node. So we see a lot of plus signs. And when we ran our KVL path around here, this was plus and minus. So you can easily see what this link voltage is. Here is the numerator. And the same thing here. Even when we're working with the supernode, this branch here we're using, and we really got to look at our initial circuit too when we're working with this, because we got our 0.5 ohm resistor here. We're using current leaving the node, so we got a plus here and a minus here. When we work this KVL path, we have a drop, rise, and a rise, so it's going to be a Vy minus 1, a simple KVL equation. There's no Ohm's law involved. This is a straight KVL. We're working strictly with voltages. There's no other signs to consider here. We have a V drop, a V rise, and a V rise. And so Vy is on the left side. If we had our V rises equal to V drops, this is really easy to realize. And the same thing with this numerator and this one too. It looks a little more tricky than a regular reference node analysis. There's a lot more work to set up the tree branches and the co-tree, but the books tell how to do all that. Just trying to show some more of the inner workings of writing the initial equations. Once we have the correct initial equations, the rest of the analysis is just a little bit of math crunch. So if we can get to here, we're pretty much done anyway. And again, this format is more adaptable to matrix substitution. Notice here we don't have a 0 on this side because we have a current source right here entering the supernode. And here we have a 2 amp source entering the node. So these equations are ready for some people call it the Gaussian algebraic analysis, to solve for 2 variables, or we can use these formats and substitute into a matrix.